Good morning. Um, I've got a example problem for a two-dimensional collision. Haven't done that yet, and that's a topic that's always involved in conservation of momentum chapters. Here in the upper left-hand corner, you can see what we're doing is a two-dimensional collision involving conservation of momentum. In that case, momentum is conserved both in the x and the y direction. So we can treat those separately. Here's an example problem where we do exactly that. It's not really any different than what we've done before. Remember, a single two-dimensional problem is two one-dimensional problems. So here we've got a collision taking place at an intersection between a car coming from the left going to the right, traveling at 20 meters per second, I hat, okay, to the right in the x direction, and a truck moving up to the intersection vertically in the image, perpendicular to the car, and it's traveling at a speed of 10 meters per second, j hat, positive y direction. Okay, they hit, this little star thing represents where they collide, and then they slide off together at some new final velocity. We're assuming this is a frictionless situation where the road is not really interacting. Okay, so we've got a final velocity. We'd like to know what that final velocity is, and also the angle, the direction that it's moving off at, not only the speed, but the direction of velocity. So here's the mass of the car. It's 10 to the third kilograms. That's 1 metric ton. The mass of the truck is twice as great, so it's 2 metric tons or 2,000 kilograms. Okay, so we have to use conservation of momentum to solve for this, and if we do so, the initial momentum is going to be the momentum of the car initially plus the momentum of the truck initially. And if we plug in the numbers that are given in the problem, mass times velocity, we get 2 times 10 to the fourth kilograms meters per second in the I hat, plus 2 times 10 to the fourth kilograms meters per second in the j hat direction. The final momentum has to be equal to the initial momentum, so the final momentum is also this value. Notice I've factored out the common factor in the two terms, I hat and j hat. Now we can solve for the angle, the final angle that they move off at. Is going to be the inverse tangent of the y component of the final momentum over the initial component, the final momentum in the y direction divided by the final momentum in the x direction, the y component over the x component. And if we do that, we get the inverse tangent of 1, which is 45 degrees. So if the truck's going north and the car's going east, then once they collide, since they have equal amounts of momentum perpendicular to each other, they slide off toward the northeast, 45 degrees to the positive x direction. Now I can use the Pythagorean theorem to solve for the magnitude of the final velocity, or final momentum, and that's going to be equal to the square root of the x component squared plus the y component squared of the final momentum. And if we do that, we get 2.8 times 10 to the fourth kilograms meters per second. And now if we set that magnitude of the final momentum equal to the total mass times the final velocity, which is fine, this definition of momentum, mass times velocity, and we want to solve for the final velocity, all we have to do is take the total magnitude of the final momentum divided by the total mass of the single object. Now the two have melded together basically, and so you get 2.8 times 10 to the fourth kilograms meters per second divided by 3 times 10 to the third kilograms. That's the combined mass of both objects. They're acting as a single object now. And you get 9.3 meters per second. So you get the final speed and you get the final direction. And there's an example of a two-dimensional conservation of momentum problem. Okay, and I've got the rocket equation here that I've derived. I start up here in the upper right-hand corner, and we've got a rocket that has an initial mass m. It's moving, it's just coasting along at a constant speed v out in empty space somewhere. then it fires its motors for a short pulse. And in doing so, it has to release gas out the back, and the velocity of the gas with respect to somebody who's stationary with respect to the rocket is going to be the original speed of the rocket minus the exhaust speed. U here represents the exhaust speed. Typical exhaust speeds, I worked on the shuttle program, typical exhaust speeds of the solid rocket exhaust was about 2 kilometers per second. You want that very high. Okay, so this is the, so now the new mass of the rocket, because it's dumped some of its material overboard, is m plus dm, a change in mass. Now there's a plus sign there. Remember, dm can be a negative value. It's a variable here, so it can be positive or negative. It's actually negative for the rocket. So the corresponding change in mass is over here. Where did it go? It's the exhaust, right? So whatever the change in mass was here, it has to be the negative value here. So actually you've got a decrease in mass here. So the mass that was lost, well, that was the exhaust mass. So hence the negative sign in front of the dm, representing the mass of the exhausted, of the exhaust. Okay. Now, conservation of momentum tells you that the initial momentum of the rocket has to be equal to the final momentum of the rocket plus the exhaust. So here's the initial momentum of the rocket, easy enough, just its initial mass times its velocity, just m times v. The final momentum of the rocket's a little more complicated. There's 2 parts to it. And that will be the momentum due to the rocket itself, okay? It's got a mass plus its change in mass times the quantity, its new velocity plus its change in velocity due to the exhausted mass, right? It's going to speed up when you dump some stuff in the opposing direction, and that's the small change in velocity dm. Now, plus the momentum of the exhausted gas. So that's going to be the velocity of the gas with respect to somebody who's stationary with respect to the spacecraft. So that's the velocity of the spacecraft initially minus the exhaust speed, okay? And then multiplied by the mass of the exhaust, which is negative dm, okay? Now, if you go ahead and FOIL this out and set the initial equal to the final, you get this right here, okay? These 2 lines, I didn't have room here. So here's the initial mass, mv, and then if you FOIL this, you get mv, okay? So notice these 2 terms can cancel on both sides. Then m times dv, that's this term. Then v times dm, that's this term. Then dm dv, that's this term. And then over here, we'll have minus v dm and plus u dm. Now this simplifies a lot. These 2 terms cancel. This term, dm dv, remember dm is already infinitesimal, dv is infinitesimal. What's infinitesimal squared? Basically 0, okay? So that term goes away. So all you're left with, and this term, negative vdm and positive vdm cancel. So all you're left with is a 0 on one side of the equation and these 2 terms on the other side, m dv plus u dm. Now I'm going to rearrange that over here. So I've got m dv on one side and negative u dm on the other, okay? Now I'm going to go over here first in this little block, and I'm going to divide both sides of this equation by dt, where dt is a small interval of time between picture 1 and picture 2 over here, the time that it took to exhaust the gas, okay? Now, if you divide both sides of this by dt, you get m dv dt, which is just mass times acceleration. So that's the force acting on the rocket, mass times acceleration, and we call that thrust. Capital T represents thrust, okay? And then over here, we've got the negative of the exhaust speed, u, times the rate that the mass is changing of the rocket, the change in mass per unit time. Now, the negative sign tells you that the vector u is opposite the vector t. The vector t is the force vector that's pushing the rocket forward. Vector u is the exhaust velocity, which is going in the opposing direction. That's why the negative sign, Okay, so this is the first equation, the first rocket equation. It shows the amount of thrust you get in a rocket. What is it dependent on? How fast the gas is coming out, U, and how quickly it's coming out, basically. So, I'm sorry, how fast the mass is being ejected. So, kilograms per unit time, kilograms per second. To give you an example, the exhaust speed of a solid rocket booster for the shuttle was about 2 kilometers per second. The rate that the mass was exhausted, to give you an idea, each solid rocket booster started before it burned with a mass of about 3 million pounds, and by the time it had finished burning, about 3 minutes later, it was down to about 1/10 of that, about 300,000 pounds. Okay, so it lost 2.7 million pounds in 180 seconds. Okay, so you could convert that to kilograms and divide that by the 180 seconds, and that would be dmdt, and then multiply that by 2 kilometers per second, or 2,000 meters per second. You would get a number of newtons. It's a huge number of newtons, measured in the millions of newtons, obviously, and that would be the thrust of each one of the individual solid rocket boosters. Of course, there were 2 of them on the shuttle, and then also 3 main engines on the backside of the orbiter. Okay, so that's how you determine the thrust of a rocket. Now, the other important property of a rocket is how quickly, or how much change in velocity the rocket is capable of. In order to find that, what we do is we take this equation, okay, which we got from over here, remember, and then divide through by m on both sides, and then integrate both sides. So dv becomes the integral dv, integrated from the initial to the final velocity, which is just the change in velocity, v final minus v initial. And then over here, u is a constant, so it can come outside the integral sign. So we've got negative u dm over m, integrated from the initial to the final mass of the rocket. Now, this is going to be a natural log. And if we, and what I did was I changed the order of, I changed the order of the limits, and I could change the sign that way, right? Okay, so I got rid of the negative sign, changing the limits here. Go ahead and do the integration, and the right-hand side of this equation becomes u natural log initial over final mass. So if you want to find the delta V capability of a rocket, you need to know the exhaust speed. Once again, the exhaust speed, very important. And the ratio, the natural log of the ratio of the initial to the final mass. So it's not uncommon for the final mass of a rocket, the part that actually makes it to orbit, compared with the amount on the ground, is only about 5%. Okay, so this ratio would be 20. Okay, the initial mass on the pad to the final mass that actually makes it to orbit. So natural log of 20, whatever that is. Okay, so this is the second rocket equation. Both very interesting to use. I'll do some example problems later.